I live in England. Oh yeah. I did for like 2 years. Yeah. I got your hopes.
Are grades in on the classroom?
No, I've just graded one classes. I've finished the front page of your test. I haven't finished the back page yet.
We don't have to read them. Yeah, I mean, if you don't feel like it, it's fine.
I mean, they're gonna get graded eventually.
You just not grade the radical strength part.
Yeah.
Not grade all of
Can you just read the front part and we're good? Yeah.
all of it.
Well, I mean, it's all gonna get graded.
Yeah, maybe just count.
I think you just count what you did right.
Yeah. So you could do like 10 out of 10 for everybody because we all tried. Exactly.
Ah, I see.
Yeah.
I'll take that under advisement.
Uh-huh.
Give it all due consideration.
Especially because parents get
Yeah, well, they're next week, right?
Oh.
Wait, can I just grade them for you? Like, can one of us grade them for you? You're not gonna be an asshole.
Yeah. Matia should do it. Yeah. Matia's got this.
All right. So let's start talking about the next topic here. So the next set of topics we're going to look at are exponential and logarithmic functions, which sounds scary. It's not as scary as it sounds. So the first half of this chapter, we're going to focus on exponential functions. And then we will connect that idea to logarithmic, talk about logarithmics a little bit, and then circle back and do some exponential stuff again at the end once we have logarithms to kind of make our life a little bit easier. But for today, the main focus is just going to be on some vocab and notation, and then talking about how to graph exponential functions and find their domains and ranges. So it's not should be a relatively straightforward kind of lesson. Okay? Okay. We say an exponential function can be written in the form y equals a times b to the x minus h plus k, where a is not 0, b is bigger than 0, and not equal to 1. So let's think about this for a moment. We have these 3 requirements here at the bottom. Let's first think about why we aren't allowing a to be 0. What would happen to this function if a was 0? We'd be left with just k, right? And since there's no variable there, that's like a constant function. That's not what we want to be talking about. We want to be talking about exponential functions. So that's why we're not allowing a to be 0. Next, let's look at why b needs to be a positive number. Well, let's think about this for a moment. where is the variable at in our function? It's in the exponent, right? So that variable could have any value. So it could have a value like 1/2, right? What is an exponent of 1/2 the same as? We just got done talking about this. An exponent of 1/2 is the same as what? So it would have been a good thing to remember from the previous test. A square root, right? An exponent of 1/2 is the same as a square root. And what happens when can we square root negatives? We don't get real numbers back if we do, right? So that's a problem. That's why we're requiring the b to be positive. So if we have a fractional exponent, we don't end up running into an imaginary number somewhere in there. Everybody okay there? And then the last thing we have to talk about is why we have the requirement that b can't be 1. What would this turn into if b was 1? Just a plus k, right? Because 1 to any power is still just 1, and a plus k has no variable in it. That's just a constant function. That's not what we want to be talking about. So that's why we have those 3 little requirements in there to make sure that when we talk about an exponential function, we're actually getting exponential functions and not something else. Everybody okay there? Okay. So there are 2 types of exponential functions. We have exponential growth, and then we have exponential decay. If I look at my equation for an exponential function, which value, a, b, h, or k, do you think determines whether this is going to be growing or shrinking? It's b. So let's take a very simple example here, and let's just consider y equals b to the x. In this case, a is 1, h is 0, and k is 0, right? So this is about as simple as we can get. So what kind of numbers, when I multiply them together, get bigger? Well, positive numbers, sure. We know that b has to be positive, so that's true. But not all positive numbers, when I multiply them together, necessarily get bigger. Whole numbers, okay, but there's more than just whole numbers. Whole numbers greater than 1.
Oh.
Very, very good.
Yes, sir.
So as long as that number is greater than 1, when I multiply that number together, it's going to get bigger, right? So our growth happens when b is greater than 1. Now, what kind of numbers, when I multiply them together, get smaller?
Less than 1.
Numbers between, well, be careful with 0, between 0 and 1, right? So fractions is kind of true, but there can be fractions that are bigger than 1.
Yeah.
You need
Fractions of 1.
Yeah, you need proper fractions, so things that are less than 1. Everybody okay with that idea? So just as a quick little example, let's run through and just determine whether these are growth or decay. Yeah, so Nancy says that this is growth. How could you tell, Nancy? Because b is 6, and that's bigger than 1. Very good. How about this one? Growth or decay? Decay, good. Why? Yeah, the b is 0.25, which is less than 1. Do we feel okay about picking out whether something is growth or decay? It's pretty easy, right? All we have to do is identify the b value, and it should be easy to see that. So exponential functions are quite important, as there's a lot of real life behaviors that can be described using an exponential function. How many of you guys are in a, well, it's probably done in a chemistry class? How many of you are in a chemistry class right now? Okay. You guys talked about, can you think of anything from chemistry that might be described using an exponential function? You guys talked about radioactive decay? You haven't done that yet? Okay. So do you know what radioactive decay is? So let's say you have a radioactive element. One of the descriptors we have for a radioactive element is its half-life. What the half-life is it's the amount of time it takes for half of that element to decay into something else. So what the element does is it emits some particles, and depending on the type of radiation, it turns into some other kind of element, right? So that happens exponentially. So the exponentially means that if it's decay, it happens real fast in the beginning and then it slows down. So there's been several little like nuclear reactor accidents that have happened over the years. There's a very famous one in Chernobyl, that they made. There was an HBO miniseries recently that you may or may not have noticed. You watched it? Okay. But there was a major problem a few years ago where there was a tsunami that hit Japan and damaged one of their nuclear reactors there and had not nearly the same amount of issue, but some radioactive material was released. So this is kind of an important issue in terms of figuring out how long before it's going to be safe for people to kind of re-inhabit these areas. So exponential growth. How many of you guys have had a biology class recently? Okay. Can you think of anything from your biology class that might be described exponentially? Population. That's exactly right. So population often grows exponentially, at least until other factors are introduced that, cause some that stop that. But those are two very common examples of exponential or real life situations that can be described exponentially. How many of you are in econ class or have taken an econ class? Can you think of anything from economics that could be described exponentially? Money. Need to be a little bit more specific than that.
Supply and demand.
No, that's not really what I'm thinking of.
It's like one of those graphs that's
inflation.
How about savings? So if you have like a savings account, the compound interest that's occurring is going to cause that savings account to grow exponentially. So those are probably the three most common settings where we're going to experience some an exponential function that we can use to describe these sorts of situations. And probably some of these we've at least kind of run into a little bit in the course of our studies here in the last couple of years. Okay. To graph an exponential function, we need to make a 5-point table, XY table. And the way we're going to choose our x's is going to be as follows. And then we can find our y's. That's the wrong spot. Now, why are we going to want to be a little bit careful about how we're choosing our x's here for an exponential function? So one of the key features for an exponential function is that it grows or decays very, very swiftly. And it's very easy, if we're not careful about how we're choosing our values, that we're going to get things that are just really infeasible to graph. Like, oh, I'll pick x equals 7. The y coordinate's like 10,037. And when I picked 1, it was 12. You know, like, good luck trying to plot those 2 points on the same set of axes. Like, that's not very realistic. So that's why we're going to be a little bit careful here. If we choose our x's in this fashion, typically our y's are never going to get too big or too small to where it's infeasible to get them on the same set of axes. So we're going to make our 5-point XY table that we've described here. The second thing we're going to do is identify what's called a horizontal asymptote. And I'm going to abbreviate that as HA for the most part, because that's a mouthful there. That's times. I'll just take out the dot. It's probably clearer if I do it that way, right?
Yeah.
So what is an asymptote? So from a graphic perspective, an asymptote is a line that the graph approaches but does not cross. Or maybe we can say does not touch. So how do we find that horizontal asymptote in the case of our exponential function? It's very easy It's just going to be y equals k. All right. So let's look at an example here. So let's say I want to graph 3 times 2 to the x plus 1 minus 4. So real quick, let's write down our values for a, b, h, and k. What's our value for a?
2. No.
3. And then b?
2.
That's 2. H, be careful, -1. Remember, the h's are always the opposite sign. Yep. And then the k is -4. So just as an aside, is this growth or decay? This is growth, since the b value is greater than 1. So if I make my xy table then, I'm going to do -2 plus h, -1 plus h. And notice that I just wrote it as a subtraction because I'm adding a negative, so it's fine to do that. I have h. I have +1 plus h and +2 plus h. And if I wanted to, I can simplify these down like so. So then I'll do a times b to the -2 minus 4. And we'll just type that into our calculator to get a decimal for that. I guess I could do it in my head. It's not that hard, but let's type it in the calculator just so you guys can see it, because this is probably something you wouldn't want to do in your head. I typed in my calculator just like it looks on my sheet of paper, and I get -3.25. They give me -2.5. It's -1. It's going to give me 2. And then the last one gives me 8. Again, if you didn't want to do those in your head, you just type them in the calculator just like I showed you a moment ago, right? All right, so let's go ahead and draw our graph. Oops, we're not done yet. So we have our table. What else do we need though?
Horizontal asymptote.
Yep, very good. Horizontal asymptote, which we can find by y equals k. So in this case, that's just y equals -4. All right. Now let's draw our graph. So I've drawn in some tick marks. Next, I like to draw in my asymptote. So the convention is when we draw in our asymptote, we just use a dashed line like this. And now I'll start plotting. So I have -3, -3.25, somewhere down here. And then I have -2 and -2.5, so that's about there. And I have -1, -1, which is about there. And I have 0, 2, which is there, and 1, 8, which is like up there. Okay. So I'm going to connect these points now. For an exponential function, we can always be able to connect this. We're going to have arrows at both ends of our graph. I want to point out to you guys here, you'll notice that my graph and my asymptote are almost parallel at one end of my graph. You guys can see that? I'm going to be picky when I'm looking at your guys' pictures about whether your graph crosses that asymptote or not. So please make sure you're drawing enough of the graph so it looks like it's going parallel to the asymptote, and you just don't start and draw an arrow that looks like it should be extending to overlap the asymptote. So for example, if you drew something like this, that's not very good, right? It looks like that arrow is going to be crossing the asymptote if we extend the graph. You guys can kind of see that. I would be picky about that. That won't fly.
No flying. That is not flying here.
No. So, okay. We should also now talk about the domain and range here. So the domain is about which coordinate, the x or the y? X. Okay. So notice that I have an arrow at the left end of my graph. So where does my domain start at? -infinity. And I have an arrow at the right end of my graph. So my domain should end at +infinity, and the line is connected in between the two arrows, right? So there's my domain. And that domain is going to be true for all exponential functions. All exponential functions, the domain will be -infinity to +infinity. The range is about which coordinate? The y. Is there a smallest y coordinate here? Yeah, what would it be? Okay. So should I have a bracket on the -4 or should it be a parenthesis? It should be a parenthesis. So what does the parenthesis mean versus the bracket? The parenthesis means that number is not included versus the bracket meaning that number is included. Can we have a point that has the y coordinate -4? No, because if we did, where would it be at? Would be on the asymptote. We're not allowed to touch that, but we can get right up next to it, like -3.999999999999999 is okay. You know what I mean?
Yeah.
So that's what the parenthesis in front means. Everybody's okay with that? All right. Is there a highest or a largest y coordinate here? No, right? Because we have an arrow pointing up. So what is the end of my range here? +infinity. So in general, it goes like this. If the a is positive, then we're going to go from k to positive infinity. And if a is negative, we're going to go from negative infinity up to k. Almost like the square root functions we graphed last chapter, right? What's the only difference there in the ranges? So we have a parenthesis on k instead of a bracket, but it's almost the exact same thing. Okay. Let's do another example. Double check something real quick. All right. So, how do we start? Well, let's list our values for a, b, h, and k real quick, and then we'll make our table. So, what are those values? Everybody happy with that? Is this growth or decay? Decay. All right. So now let's make our table. So we're going to have -2 plus h, -1 plus h, 1 plus h, and then 2 plus h. And notice again, I said plus and wrote subtraction because I'm adding a negative, which is the same thing as minusing, right? Everybody happy there? Okay. Now for our y coordinates, it's a times b to the -2 plus k. So if I do that, I get 8. And we have 3, or a times b to the -1 minus 4. If I do that, I get 2. Then I just have a minus, or a plus k. It's -1. I have a to the +1 minus 4. That's -2.5. And then ab squared minus, or plus k gives me -3.25. And again, if you're can't do those in your head, just type into your calculator exactly as it looks. Everybody's okay with that? All right. Before I draw my graph, let's write down our horizontal asymptote. What's that going to be this time? Y equals -4. Okay. So there I've drawn my XY axis and put some tick marks in. Next thing I like to do is I like to put in that horizontal asymptote. And I'm going to draw my graph. So -3, 8. -2, 2. -1, -1. Then I have 0, -2.5. And then I have 2, -3.5. That up here. Everybody happy with our picture here? What's the domain for this picture gonna, or for this graph gonna be? It's exponential, so it's always negative infinity to positive infinity. And what's the range gonna be here? K to positive infinity. Again, because the A value is positive, it's just K to positive infinity. Everybody okay with this? So let's quickly here compare what these two graphs look like, because we have one that's growth and one that's decay. Everybody's okay with that? So let's look at this decay graph right now. Where is the steep end of our graph, on the left or the right? The left. Where is the flat end of the graph? On the right. Now let's go keep that in mind and let's look at the growth one. So which end is the steep end? The right. Which end is the flat end? Left. So they're opposite in that regard. And that's kind of an easy way to visually identify a graph as growth or decay. Is everybody okay with that? So growth, the flat end is on the left and the steep end is on the right. And decay is the vice versa, the opposite. How do you guys feel about this? Should be okay, right? Not too bad. We're going to stop here.